So ladies and gentlemen, it's 2026 and you are writing the next great American novel or the great next Python library. You might even publish it on PyPI. And you've heard about this nogil thing and you're like, you know what, I should embrace the future. I should make my library multi-threaded cooperative, like it should work in a multi-threaded environment. And so you look into it and it's like, you know what, all I really need to do is add a couple of locks. And honestly, that is probably enough for most people. But sometimes life gets a little bit more complicated than that. And you might have a race condition somewhere. And a race condition, again, it's not the end of the world. It's a solvable problem. Often you just need to add a little bit of extra code to recognize when the race condition is happening, and then you write a little code to handle the race condition, and you're off to the races. Oh, my friend has brought my jacket. It's really cold in here. So you write a little code to handle the race condition, and you're fine. But now you have another problem. Thank you very much. Oh, perfect. This will be nicer. Now I won't freeze to death. Now you have another problem. Not that you have the race condition problem, but now you have a software engineering problem because it's 2026 and best practice is you should have a unit test suite that achieves 100% coverage. If you have a line that only gets run very rarely when a weird thing happens and it's out of your control, how do you make a 100% reproducible unit test suite? So now this 99% is sitting there mocking you. You can't sleep at night. You failed. Your life is over. What are you going to do? The answer is you're going to get it to 100% because you're going to use something called Blanket. And that's what I'm talking about today. It is a new library. I gave this talk, again, 10:30 in the morning yesterday. I shipped Blanket for the first time at 11:30 the previous night, and I finished the talk at 2 a.m. So this is just-in-time software. Why is it named Blanket? Because it is coverage using threads. Thank you. Thank you. So when you use the threading module, you are giving yourself a problem. I mean, this is a little glib, but fundamentally, you're going to be using lock, rlock, condition, event, barrier, semaphore, and bounded semaphore. And all of these things are going to help you synchronize between your threads, but they themselves also behave in a non-deterministic fashion. If you have 3 threads that all call into a lock and try and, like, you know, they want to acquire the lock, what order do they get the lock in? And the answer is, I don't know. You're going to do whatever the operating system scheduler wants you to do, in fact. That's really the scheduler is going to decide, and who knows what its thought processes are. It has all sorts of state, is a complete black box to us. So you cannot predict what order your threads are going to run in. You need to solve this and replace it with deterministic replacements from Blanket. And that's going to make your program deterministic, and now you're going to be able to control the order of events, and you're going to be able to make any you're going to make any race condition reproducible on demand. So I'm going to walk you through the process. We're going to look at a test program. I have written it twice. The first time is with the threading module. It's a little long. I apologize. It goes across 2 slides. This is the first page. First page, we're going to import random for fun, and threading, of course. And we're going to create a lock and a barrier. And if you're not familiar with a barrier, we've given a number. That's the number 3 here. That means how many waiters we need to release the barrier. The way that the barrier works is you call barrier.wait. First guy who gets there, he just waits. Second guy who calls it, he's going to wait too. The third guy who calls barrier wait, now we have 3. The barrier opens, and all 3 of them make progress at the same time. So the barrier synchronizes multiple people and releases them all at once. So this is our worker thread at the bottom there. With lock, and then I print, I got the lock. And then I wait for the barrier, and then I print, I got through the barrier. Second page, we're going to create our 3 threads, A, B, and C. That's my convention. I name threads with a capital letter. So when you see a capital letter by itself on the slides, that's going to be a thread. And we run it, we create the threads, and then we stick them in a list, and we shuffle the list, just to add some more randomness to this, just to make sure that we've got things nice and random for our lives, right? And then we start all the threads, and then we join the threads. And when you join a thread, that just means you wait until the thread finishes. That's good for cleanup. If a thread is running when you try and shut down the process, like you can try and print a standard out and it's already been shut down and you get errors, it's terrible. So it's a good policy to wait for your threads to exit. So when you run this program, you're going to get this output, or maybe this output, or maybe this output. They're going to run in all sorts of different orders. If you have 3 threads all trying to access a lock, there are 6 possible orderings of those 3 threads acquiring the lock. If you have 3 threads trying to get through a barrier, there are 6 possible orderings of the 3 threads resuming after they get through the barrier. 6 times 6 is 36. So there are 36 possible ways to arrange the A's and B's and C's in this output, and you never know which one you're going to get when you run this thing. You're going to get one of 36 every time. If you have a race condition that only happens when they happen in a particular order, A, B, C, how do you make it happen on demand? The answer, of course, you were expecting this is use blanket. So this is the same script. I've rewritten it using blanket. The lines that are in bold are the ones that I have changed from the threading original. So we're going to import blanket. And now instead of creating a threading lock, we're going to create the scenario object. I'm going to tell you all about it in a minute. Let's just let it ride. The blanket scenario, that's our scenario. And then we create the lock and the barrier off of the scenario. Then on the second page, this is all the same. None of this has changed from the previous one. We're going to create the worker thread, which is exactly the same. We're going to create our threads and shuffle them, which is exactly the same. And finally, we've got some more excitement. Here's some more blankety stuff. We're going to create these, what I call API objects. So you'll notice we call API and we pass in the lock. That is giving us a control surface to control the lock's behavior. So we have an API surface for the lock, which we're going to use to control it. You'll notice the worker never sees. The worker is only going to see the real lock. We do the same for the barrier. So now we have a control surface for the barrier. And now we have a with scenario block. I'm going to call this enter the scenario. We are going to enter the scenario. I'll tell you why in a minute. Inside of the scenario, we start our threads, and then we call some funny looking functions here. And these are what is really doing the work here. These are what I call high-level APIs in Blanket. The first one is lock API relay. Relay on a lock on the control surface says, I have a couple of threads and I need to step them through acquire, release, acquire, release, acquire, release. So these are going to acquire and release the thread, the lock in the order BAC. It doesn't actually call release on the last one, so we have to add an extra unblock for the last one, just to clean up after ourselves. So that allows C to make progress from its lock release call. And then we have the barrier. Barrier has, the high-level API has an API called cycle. That runs us through a wait and everybody runs cycle. Wait and everybody runs. Like condition does that, event does that, barrier does that. So in the case of barrier, you just specify the wait threads. In this case, C, A, and B. Inside of the with statement, you could actually use the value that comes back, the cycle object, and you could explicitly wake up the threads in any order you want. If you don't do anything, you get the order that you specified them in when you called cycle. That's actually the order that they approach the barrier, and if you don't do anything, that's also the order in which they get past the barrier. So what I want you to remember from this slide is BAC, CAB. And then we just join the threads when we're done. And this is the output you get, BAC, CAB, every single time. We have now taken away the non-determinism that we got from using the threading synchronization primitives. We replaced it with complete determinism controlled by blanket. Now you can reproduce your unit test cases that have funny race conditions or require things to happen in a particular order, anything you need, because you are now in control of the order of operations. So we're going to talk about the scenario object. We already imported blanket and created this scenario. The scenario is the object at the root of everything. All of your interactions with blanket and all of the objects that come out of it all go back to the scenario. It's control of everything at the top. So that is where you're going to create your 7, and believe me, I know these backwards and forwards. Lock, rlock, event, barrier, condition semaphore, and bounded semaphore. Those are all created off of the scenario object. And by the way, these are classes, but they are also bound to the scenario instance. If you call scenario.lock, you get a lock object that knows about the scenario. It's kind of like a method. If you have a function and it's inside of a class and you access it through an instance, you get a bound method, right? This is a bound class. I think that's really cool, and I've been using this for years and nobody seems to care. I don't understand it. This is called a bound inner class. I have them in my big library. I think they're fantastic. It solves all these problems. It's great, but I still work in obscurity. So the objects that you get back from the blanket look like the real thing. I call this masquerading. So if you create a lock from threading or a lock from scenario, the repers look the same. There's actually one little tell. If you see a repr for a lock and you're like, is that a blanket repr or a real threading lock? If you can't tell the difference, I have uppercased the ID. So that's your little tell. If you're just looking at it, you can tell the difference between a blanket lock and a real lock. But what's interesting is you can't tell by saying, is this an instance of a threading lock? Because they both say true. That's a Dunder class as a property, a read-only property that returns threading lock will do this masquerading thing. However, if you want to know programmatically, is this a blanket lock? You just say is instance blanket lock, and the threading lock will fail and the blanket lock will pass. So you can tell if you know how to ask. So we're going to talk about all of the stuff that Scenario will do for you. Fundamentally, Scenario and Blanket is about synchronizing with these objects. And the hardest part about Blanket, honestly, there were a lot of hard parts, but the thing that really stressed me was figuring out an API that was convenient to use, because writing the code that regulates the behavior of all these things, it got big really quick. And I worked very hard to make it smaller and make it more manageable. So the way that this works is, I have 3 layers conceptually, which unsurprisingly are the low, medium, and high level layers. So we're going to walk you through all of those, because while you're using Blanket, you're usually going to stick with the high level abstraction, and that's going to be very convenient. But it's important to understand the low level abstractions underneath you, because all abstractions are leaky sooner or later. And so it's important that you understand how Blanket works, so that when something goes a little bit sideways, you're like, okay, well, I understand this area generally, and I can probably figure this out. So I say that Blanket is founded on 2 foundational low-level concepts. The first one is the transaction. A transaction is an object that represents a particular call to a particular method on a particular primitive at a particular time. So if this thread calls lock.acquire, that's this thread, this lock object, and it's calling acquire. We have an object that represents that, and that's the transaction. So transactions are created all the time under the covers. You can inspect transactions in flight. I was just lazy when I wrote this slide, so I said, there's a log of all the transactions that happen in the scenario, and I just run a transaction and then grab it out of the log. So this is creating a lock, calling acquire on it, and then we get the last transaction out of the log, and we print it out for you. So this is the repr of the transaction object. This is telling us we called lock acquire. It is currently in state returned. It ran on the main thread. It started at this particular time. The result was true. That's either the return value or the exception it raised if it raised an exception. It is not currently blocking, and this was done for lock number 1. I internally give all the locks and all the things names, and you can rename them if you want, which actually makes your reprs much prettier. So that can make it much easier to read the output of these tests when you write them. Transactions are state machines. There are actually 10 states. One thing about the transaction state machine I was very careful about, you only ever go forwards. You never go backwards. It is always, if you are in a particular state, you know you will never visit a previous state. Under normal circumstances, if you're just using a transaction directly, you're sitting around, you're just running transactions without entering the scenario, and we're going to talk about that. But if you're using one normally, you just commit it, which is to say you call the real method, and then you go to return state. So you're kind of done. But when you enter the scenario, something magical happens. This is where the Blanket stuff really starts to take over. Inside of the scenario, all of the synchronization objects that you created with Blanket, I say they go from unregulated to regulated. And there are 2 extra things that happen. There's a new state called blocked, and there's a new state called paused. These are what are called parking states. There's a terminology I'm borrowing from Java here. I've been programming this with AI the whole time, and the AI was just calling this, you're parking the thread, you're parking the thread. I said, what is that? To park a thread means you're going to call something that blocks and waits until somebody else says you're allowed to proceed. They say we give it a permit. So it parks, and then it gets a permit, and it's allowed to make progress. So that's what I'm doing here. When you call lock.acquire, and you are inside of the scenario, the first thing that happens is it stops and waits. It waits for permission, in this case, from you, to proceed. So the way that you write your tests when you're writing with Blanket, you do all of your work inside of worker threads. And then the main thread, the guy who is running the unit test suite, he says with scenario, boom, and now I say he has taken on the role of the scheduler. He has become the scheduler. And the scheduler is the guy who directs traffic for all of these different synchronization objects that are participating in the test. And he is saying, I want this order, this order, this order. This should have happened, this should have happened. And you might be asserting state, but mostly you're going to be just regulating state. And once you're done with all that stuff, then you exit the scenario, and then you run your assertions and see if the test worked. And that is really the most surprising. Oh, that's my slide here. I'm just sort of pointing out commit is occasionally a parking state as well. Life is complicated with the threading module. So the most surprising thing that I've figured out when I was working on Blanket was that this is all you need. When I originally started writing Blanket, I thought that I needed to completely simulate all of these objects. I needed to write replacements, and you got total control of the replacements. You don't need it. All you need is the block before and the block after. I call it the block and the pause, just to give them names so that I can talk about them sensibly. If you block before every method call, that is the bread and butter of Blanket. That is the thing that gives you control over when things happen next. You don't need to control the internal state of the lock. You just need to control who calls the lock in what order, and that implicitly controls the internal state of the lock. And so all you need is this external control. So I was shocked that that was all you needed. But in point of fact, that means that Blanket is not re-implementing these things. It is using the real locks and barriers and condition event objects underneath. When you call lock.acquire in a Blanket lock, you are eventually calling block.acquire on a real Python lock underneath. I'm just wrapping it and maybe parking before and maybe parking after. I skipped over it a minute ago. So blocking before is the bread and butter. That's what gets you all of the behavior of controlling when the order of operations happen, when the state changes inside of these objects. Controlling the pause after, that's how you control when the thread resumes after doing the work. So when the three threads call barrier.wait releases all of them, and then what I do is I set them all to pause, and I allow them to release in the order that you asked for. So that's how we control the order of resumption after the barrier wait. So I said there are two fundamental technologies at the heart of Blanket. The first one is the transaction. The second one is called scenario.wait. This is a method call on the scenario. This is modeled after a wonderful API from Win32 called wait for multiple objects. The way that this works is you call wait and you specify a number of, I call it an item. Really, it's maybe more accurate to say it is a signaling object. These are objects that represent a signal that is either high or low. It is either true or false. It's a binary signal. And if all of them are false, then you sleep. And you wait until at least one of them becomes true. At the moment any of them becomes true, scenario.wait is going to exit. When it exits, it returns a set that I'm calling signaled here. You can call it whatever you like. But this is going to contain the set of signals that we're signaling. So what are some examples of things that could signal? Well, you can pass in a thread handle. When you pass in the thread signals if a transaction is running on it. So now you can wait until a transaction happens, and when one happens, you're going to wake up, and now you can look at the thread and see what the transaction was. But there's something you can wrap a thread handle with. You can say, if the thread has terminated, I want to know. So this will signal if the thread has terminated. You can also wait on I don't remember my own slides. You can wait on something called call, which says this thread is calling this method on this object. This is a specific lock, and we're calling acquire on the lock. This will signal if this thread calls acquire on this lock. Yes, this will signal if this thread calls acquire on this lock. You can wait on a transaction handle. A transaction handle signals when it is done. So you can wait for a transaction to be over. You just pass in the transaction handle. And there are some things based on the transaction handle too, like paused, for example. This will signal when this transaction is in the paused state. It only signals when it's in the paused state. It stops signaling when we leave the paused state. And then there are some signals that you can negate. So you can say, for instance, not terminated thread, and that is signaling true while the thread is running, and it stops signaling when the thread exits. So now we're going to rewrite our test using just the low-level APIs inside of Blanket, and then I'm going to walk you up the conceptual thing from the low level to the high level. So we're actually going to rewrite this thing, I don't remember, I think it's maybe 5 times. The first page is always going to be the same. So this is the first page of the test. We import Blanket. We create our scenario, and this time we're going to drop we don't need to demonstrate it now, so we're just going to do the lock. So we have a blanket, we create a scenario, we create the lock. Here is our worker. All it does is lock the lock and print, I locked the lock. And we're going to create our threads. Again, all of this is going to be the same. I'm going to show you the second page, and we're going to rewrite the second page about 5 times. Here's our first one, only using the low-level functions. This is a really simple scenario script. It is kind of, I will say, it's not paying attention to what the thread is actually doing. So for instance, there's nothing in here that says, I know that you're supposed to be calling lock acquire right now. But again, Blanket has made this program 100% deterministic. We know without looking that the thread is going to be running lock.acquire and then lock.release. Because it's completely deterministic, we actually kind of don't need to assert it. The higher level APIs do assert this stuff just to make sure everything is working okay, but you kind of don't need it. So what we're doing here, we iterate over the 3 threads, B, A, C, in that order. And then we do these following operations twice. That's what the for loop is for, the nested one. We wait on the thread. That means that we wait until a transaction is happening. That means we wait until the thread calls a method on one of the blanket controlled objects. Then we pluck out the transaction. We ask the scenario, give me the transaction that's running on this thread right now. I abbreviate transaction as TX a lot. I think you've already seen it. Then we unblock the transaction. What's happened here is the first thing that happens, we're inside of the scenario so that when you run lock.acquire, it's going to hit the blocked state and park. Unblock releases the park. So this is going to allow the thread to make progress on running whatever transaction it is. The first one's going to be lock.acquire. The second one's going to be lock.release. And then we wait for the transaction to finish. Wait on the transaction, and we only wait on one thing. When it returns, we know the transaction is done. So this is going to safely drive the thread through the lock acquire and then the lock release, and then it's going to do it for the second one, and then it's going to do it for the third one. So when you run this script, you get VAC got the lock, and you always get this order. All 5 of our demonstration scripts are going to produce the same output, so I'm not going to show it to you again. So let's move slightly higher up the food chain. This is, again, the second page of our test script. We're going to create a lock API this time, and we're going to do it with a lock API. So with scenario, now we're inside of the scenario. Now all of the objects are regulated. By the way, I forgot to call something out. I didn't forget yesterday morning. On this first page, when we create the threads, we're not creating them using threading.thread anymore. We're calling a helper function in this scenario called thread, funnily enough. You specify the function you want to run in the thread, and then in star args and star KW args, I just pass straight through to the thread object. And this is what I call a managed thread. Scenario is managing this thread for you. When you enter the scenario, it starts the threads automatically. When you exit the scenario, when you leave the with scenario block, it joins the threads automatically. So everything is started for you and cleaned up for you automatically. It's very nice. So that's why we're not seeing thread start or thread join on the other slides. It's being done for us automatically. Sorry, I forgot to mention it a minute ago. I don't have very good slides or notes on my slides. So we've moved to the slightly higher level version of the script. We have a lock API object. That is what gives us control over specifically this lock object. And for thread in BAC, we're going to say, hey, Mr. Lock, unblock anyone who is calling lock acquire in this list of threads. We're only going to do one thread at a time. You could actually specify multiple threads. This one is a little safer. It's going to say, we have to have a transaction. It will actually wait for a transaction to happen, and then it will say, this transaction better be a lock acquire, and if it is, it will unblock it, and we're on our way. These, by the way, this is something I added Friday afternoon. These wait automatically for you. So this waits until we get to another blocking state, and in the case of acquire, it's generally safe to do. This is written in a safe way. It's very important that you synchronize between the scheduler and the worker threads. But written in this way, and written in all the ways I'm going to show you, it is safe, it is synchronizing. So we unblock the acquire call, and then we wait for a lock release to happen. This is another signaling thing. This is actually a bound method object. If you wait on lock.release, that waits until any thread that we are observing blocks on a lock release call. So this is safely waiting for the lock.acquire to finish, and then it runs lock.release, and now we signal. And now there's a lock release transaction waiting on the thread, and we call lock unblock, lock release. And so now this is going to make progress. But now we're only 3 lines instead of 4, and it's also a little safer. But we're going to go higher still. This is what I call the medium level API. we've created now an object called driver. Driver's job is to drive threads through work. So you're going to sort of point it at a thread. In this case, you see we create the driver and we pass in thread. It only operates on one thread at a time. And when you call the driver, like d parentheses like that, you're saying, do some work, drive things until you need more instruction. Generally, in this case, it's going to look at the thread and say, oh, there's no transaction yet. It's going to wait for a transaction to appear. When the transaction appears, it's going to return, and it's like, what do you want to do now? And so we call skip. Skip says, whatever transaction's running right now, drive it to be complete, and then go into idle state and wait for another transaction to show up. So the first call to D is going to wait for a transaction to appear, and that'll be our lock acquire, because again, we're deterministic. And then the skip will drive that acquire call to completion, and then wait for its second transaction, and then we're gonna lock.release, we're gonna wait for that to happen, and then it will return to us. And then we call finish. Finish says, drive the current transaction to be done, and then go into your I'm done with everything state. Driver, you can deal with a driver individually like this if you're only driving one thing at a time. If you have multiple drivers that you want to interact with all at once, there is a higher level object called dispatch that's like a collection of drivers that it drives them all at the same time. You can also serialize them with an object called chain. So this, again, produces the same output. We've made slightly more lines, but on the other hand, we're also working at a very high level, or comparatively high level. But we're going to go even higher. We have one called skip. Skip and the other things are all built on top of drivers. So skip, the way that this works is you specify a thread followed by one or more methods, and skip is going to drive the thread through those methods in that order. So you say, hi, skip, here's a thread. It's going to be running a lock acquire, and then it's going to run lock release, and I want you to step it through all that stuff. Skip is inherently serial. It's not going to do multiple things at once. It's going to do one thing at a time. But if you don't care about the ordering of things, and it's like one thing at a time is fine, it's very convenient. But we're going to go to the highest level here, and that is this thing we saw in the first example. You remember our lock API relay. So each of the different synchronization objects has a different style of high-level API that is custom tailored to the way that it works. Lock and rlock get relay, and they get another one called assign that's like a simple version of relay. Condition, event, and barrier are condition-based, and they get something called cycle, which you saw in the barrier example. And then semaphore and bounded semaphore get something called allocate. And these are all designed to work with the idiom that the synchronization object works in. The way that relay works, again, I kind of went over it on the first slide. You're going to point it at a couple of threads, and those threads are supposed to run acquire followed by release, acquire followed by release, acquire followed by release. Actually, the first one is allowed to be just release if it's already holding the lock, and the last one, we don't bother to wait around for the release, we just acquire it. Relay is an iterator, and it yields after a thread calls lock acquire successfully and finishes. So it yields the thread that has recently acquired the lock, in case that thread goes on to do other stuff with primitives. That gives you a nice spot to like, okay, the lock has acquired, the thread has acquired the lock, and now it's going to call this other thing, and I need to drive that, and it's going to call this other thing, and I need to drive that. And then when it's done and it's about to release the lock, you just iterate, and you move on to the next thread, who's going to do the next thing. So again, it's set up to drive code that is using a lock pretty well. I think it's a pretty good API. So that is the bread and butter. That's what most of what you're going to be doing with scenarios. Blanket has a lot more features. For example, you can manage timeouts. There are a lot of functions in the synchronization objects that take a timeout, and you can say, I want to force a timeout on this guy. You call expire. Or you can say, I want you to suppress the timeout. I don't want this function to time out whether it would naturally time out or not. That's called disregard. If you want to restore the original timeout, you can say revert back to the original behavior. There's something called a raw handle. Consider, if you're inside of the scenario, you have a lock. If somebody calls that lock, they're going to block, and it's the scheduler's job to release them. What if the scheduler wants to call lock.acquire on that lock? What if you want to fiddle with the state of these synchronization objects from the scheduler while you're running the test? The answer, if you just called lock acquire, then you would block for somebody, which is supposed to be you, to unblock the lock. So I give you a raw handle. A raw handle doesn't have any of the regulation. The raw handle will just immediately do the thing, and it never blocks like that. And that brings me to the concept of core objects. The architecture of Blanket, this was really successful architectural change that I picked pretty early on. What I call the primitive, that's the lock object you have to work with threads. So there's the primitive, and there's the raw handle, which is the one that's unregulated, and then there's the API object. These are in fact all thin layers around a core object that represents the lock itself. The core object lives in the scenario core, and there is a single lock called the score lock. Score is a portmanteau of scenario core, because it turns out the scenario object that I give you itself is also an API object. It is a thin wrapper around the scenario core. Anytime you call into the core, you have to lock the score lock. So there is one lock that controls everything in Blanket. It's kind of like the GIL. And you know what? Performance is fine. The GIL is okay. I would say that the score lock is less contended than the GIL is. Like, you just have to hold it for a minute while you change some state and then you release it. So the score lock is lightly contended. It's not really hurting performance. And meanwhile, it makes everything so much easier. Everything is nice and regular and deterministic. It's a successful design choice. Anyway, it's kind of interesting that all of these objects are calling into the core and doing all their work in the core thing. All the ones that you deal with are really just very thin wrappers. They're allowed to do boxing and unboxing, and that's about it. They lock the lock, they box or unbox, whatever they're going to do, and they call it the core. Finally, well, another feature, I guess I should say, if you're thinking, okay, one of the things about Blanket is you have to be using the Blanket objects. So the way that I think that code should work is you create the thing and you give it the lock you want it to lock with, or you give it the barrier, or whatever it is. So you're going to pass that in. But maybe you have code that's written in a different style and it is actually allocating its own objects. So that means it's going to say import threading, and it's going to say threading.lock, or just lock if it said from threading import lock. So now it's creating its own objects. How do you take control of that? So what I'll let you do, I have limited, because you got to be careful with this stuff, but I allow you to monkey patch that module. So scenario.inject, you give it a module handle, and it will inject the Blanket replacements for lock, rlock, all those things at the module scope. And if I find something that says it's the threading module, then I replace it with a fake threading module that actually calls my objects, and otherwise behaves like the real threading module. And speaking of injecting, maybe it was a mistake, but I also have another thing in Blanket that is kind of unrelated to the previous thing that is also called inject. So let's say that you are some sort of galaxy-brained individual and you're writing a lockless data structure. So you're not calling lock, you're not calling barrier, but you have race conditions. You might have worse race conditions, and you want to be able to test those. What do? I have an answer for you. This is called the injector. Well, the way that the injector works is you take some Python code. It's only going to work with Python code, sorry. And you go into the bytecode and you inject a function call in the middle of the bytecode. So for example, you could inject a call to event.wait for an event call object that you have constructed. And then you call this thing, it hits the event.wait, and now you're in control. You can call event.set and allow it to make progress. And until you do, it's going to sit there and wait. The way this works is there is a location object, and you can specify, you give it the callable, and you say at this position, maybe with the line and column information, maybe based on some text that is going to be in the string associated with the bytecode. Maybe you're searching for the token itself. And worst case, you can specify an offset. But these are all pretty fragile. The worst one is especially fragile. But maybe that's what you really have to do. And then once you have this location object, you can call inject call, and that's going to inject a callable at that location in the bytecode. So now you can, if you have a lockless data structure and there's two things and they need to interleave like this in order to test them, you can insert calls to synchronization things in those points and effectively turn it into a single threaded call that's bouncing between contexts. It's like cooperative multi-threading, but it's effectively single threaded. You have reduced it to completely deterministic behavior. And that's kind of the credo of Blanket. My credo for Blanket is your test should be effectively single-threaded. And if it's not single-threaded, you haven't blanketed hard enough yet. You need to slow it down. That is everything. And I went 5 minutes over. Look, well, I don't know what I did, but okay. Do I have time for questions or a couple extra slides? Like, where's my showrunner? Where's my runner? Nobody's here answering questions. Ladies and gentlemen, it's chaos. I'm allowed to do what I like. I'm going to go into a couple extra slides just because I have them, and then I will take questions, and we'll do this until they kick me out, okay? So the first thing I want to say is there anything like blanket out there? The answer is only kind of. There is a rich area of computer science research into something that's called stateless model checking. This is like blanket, except you don't write the scheduler. Instead, they stochastically or they systematically explore the space of all the possible different combinations of going through the program. By the way, I never got to that term. I call that controlling the tempo. The tempo of your program is the ordering, the sequence of events of allowing things to make progress. So you as the scheduler control the tempo. With stateless model checking, they have an algorithm that controls the tempo that is out of sight, but they are exploring the whole space. And what I'm told is the hot area of research in here is reducing the space that they have to research because it explodes very quickly. There are example projects of this is Microsoft Chess, AWS Shuttle. There's something in Rust called Loom. The one that's closest to Blanket, I think, is called Microsoft Coyote. This runs CLR programs and it stochastically checks them, but it also emits a file that allows you to replay the events in a particular order to reproduce a crash if you get a crash. So it's kind of like Blanket, only automated if you're on the CLR. It sounds pretty good. But I don't think you can construct those yourself. You can't cause one to happen. So I don't know if you can do something like Blanket where it's like, I know this happens in this order, and so I'm going to write a scheduler that makes it happen. Another notable thing about this project was my first experience with working with AI. I wrote the whole thing with AI, and it has been an enormous amount of work and has made me enormously more productive. I will say that Blanket itself is pair programmed with AI. The tests are kind of vibe testing, and docs are kind of vibe docking. But again, I feel this has been very successful. It has been so productive, I've actually rewritten Blanket about 5 times. The original era was what I call the total control era, where the synchronization objects were like little hand puppets. They were totally inert on their own. If somebody called into one, they just waited until I decided what they were going to do. The problem with having total control over the objects is now you are forced to exert total control over the objects. So your scheduler scripts got long real quick, and I said, this is not survival. I have to figure out a way to make this simpler. So the second era was making them simpler. But this was kind of rudderless, and I'm sorry, I didn't turn off the lights. This was kind of rudderless, and it was not successful because it didn't have sort of a clear vision of what it wanted to be. It was kind of successful in finding ways to make things simpler, but during the development of it, I realized the third era, which is what I call the scheduler controls when. This was the idea, the inception of the idea that all I needed was the lock before and the lock after, and I could control everything. I still had full reimplementations of the synchronization objects because that allowed me to go in and fiddle with their state because I knew what they were. And it wasn't until late in the development of third era, when I was almost done, that I threw it away and started over because I realized all I needed was a thin wrapper. And when I say thin wrapper, blanket.py is about 8,200 lines, so it's not that thin. But I didn't have to re-implement all of these objects myself. I'm literally using a real threading lock underneath. It's just I have a lot of scaffolding around it. And I think that is probably where I'm going to call it. So if you have questions, I'm happy to answer questions. Otherwise, we're going to go find someplace warmer. Thank you. Hi, Mike.
Hi. Thanks, Larry. Very interesting talk. A short question, since you do kind of synchronize the threads, is there any kind of overhead in terms of performance, especially if you have a lot of threads that they have to wait longer for each other?
So,
or is it just...
the acoustics are terrible in here. I got performance. You want to know about
performance?
performance?
If you have a lot of threads and they wait for each other, is there any kind of performance overhead?
There is performance overhead. I'm not sure what it is because honestly, I kind of don't care about performance overhead because this is used for unit testing. Okay. I would say unit testing, and also one nice thing about Blanket, if you have a race condition and you don't know how to fix it yet, you can write a Blanket script to reproduce your race condition. So you can use it during development to make reproducible tests for things that are hard to reproduce, right? So you use it during development, but you don't use it during production. You're not going to use Blanket objects in production. Okay. So I don't really care about performance that much. It's going to have a performance impact, but again, when you're using Blanket, slow it down, make it all single-threaded. Your tests should not be performance sensitive. So I actually don't care about performance very much. That said, if it's slow and I figure out that it's slow and I can make it faster, I'll make it faster. But there are actually a lot of little weights inside of Blanket to sort of slow things down and make them synchronize better that I'm not going to take away. So Blanket is intentionally not fast. I kind of get this a lot. I talk so fast, I kind of stun everybody into silence, so I don't get questions. So please.
Yeah, I was going to ask about the naming of skip. I'm not sure I follow the logic behind that name, so I was hoping you could explain.
Sure. I spent a long time, and again, conversations with AIs about these things. Skip was popular very quickly. Skip means there's a transaction running right now, and I don't care about it, so skip over it. That's all it means. There are three there, actually. There's skip, there's park, and there's finish. Skip skips over the transaction. Park says, ignore every transaction on the thread until it calls this one, and then park it in that transaction. So if you said park thread lock.acquire, anything that it runs, oh, I got to stop. I'll finish my sentence. Anything that it runs, it's going to just skip over it until we get lock to acquire, and then it'll say, oh, that's good. That's what the user wanted. I'm done.